Hey, welcome to day 166. It's been a wild day. Had to get the internet service tech out. But here we are. So, have you ever used one of these before? Do you know what these are? This says phone induction charging. You probably haven't probably haven't thought of any of these things as what this is. Induction charging, but maybe a wireless charger for a phone. You probably thought about that. They exist. Um, So, have you ever used one of these before? And do they work? And how do they work? And are they good? Well, I have. And they vary. We're going to learn about how they work today and basically what the deal is. So, day 166. Two goals that you're able to define. Let's refresh. Three goals, actually, that you're able to define conductor and insulator, that you're able to define conduction and induction. And I lost the third one, I guess. Oh, there it is. That you're able to understand how connection-free charging pads work. How does wireless charging work? So, have you ever used wireless charging before? I pulled up this picture here. At Starbucks, you used to be able to go and check out one of these little rings and then plug it into your phone. Yeah, they had them on these little stands right here. You'd plug it into your phone, and then your phone, you could just keep it on this little thing that was on the. See, they had these little spots, or on the table, they'd have these little rings, and you could just put your phone on it, and it would charge while you were hanging out. It's cool because it was novel, right? It was new, but turns out it's really annoying because what do you want to do with your phone? Sometimes when you're sitting there having a coffee, you want to pick the phone up, right? You want to do this, and and so you want to do that, and you can't pick up the device, so the wireless charging won't work. So, an interesting thing as long as your device is sitting still. Okay. How close to the charger do you need to be? Well, this principle, we'll learn more about it in a sec, but it works really similar to, say, this thing. Remember these? All right. I can draw on here, and if I touch, you can see I'm drawing some lines. And if I get the pin pretty close, it's not even a pin, but a magnet, I can start to make this line. It's a little bit fainter. It's kind of spotty because I'm moving in and out. Similar kind of principle here. These are my kids' trains. So I get here, I can feel a pull. I get closer, stronger pull, and then click. All right. So distance is really important. This comes from Coulomb's law, the one we saw yesterday, where distance squared is in the denominator. So the further apart you are, the force gets reduced by the square of the distance. So this kind of inductive or wireless charging doesn't work very well if you're far away. By the way, there's about 50 cars now that offer wireless charging, including Teslas and many others, where you just put your phone in a spot and boop, it starts to charge. And that's pretty cool because you're not supposed to be using it while you're driving anyway. Okay, I'm supposed to define some of these things. So for that, I'm going to go to the reading. And the reading is here. And it may need to reload. So we'll wait for that. And while we're waiting for that, excuse me, I'll say I hope everybody's doing well. And here we go. Okay, so the reading's on conductors and insulators. So you probably think of things that conduct, like things that conduct heat, right? We talked about conductors and insulators there. So metals conduct heat energy pretty well, thermal energy pretty well, and insulators don't. Right, so insulators would be things like wood and styrofoam and things like that. So many of the things that are good at insulating and insulating thermal energy are also good at insulating electrical energy. So what's going on? What are we thinking about conducting and insulating? We're talking about electrons. Electrons are the things that move. And so when we talk about a conductor, it's something that allows electrons to move and insulators are things that don't allow electrons to move. Electrons are in all kinds of materials, and where are they? Well, they're in the atom. And where are they in the atom? Well, they're not in the nucleus. They're orbiting around the nucleus, and they're kind of, it says here in the book that they are free to roam. It says that they're not anchored to the nuclei, and that's true. This is often stated using the phrase that they're loosely bound. So they're bound as in they're connected, but it's loose enough that you can get them to leave. And the way we do that is charging by friction is one way. All right, that's where we drag your feet on the carpet and you touch the doorknob and you feel that static electricity neutralizing or going to equilibrium. So reading through here, you'll want to be looking at the guided reading when you're doing this, because the first thing in the guided reading basically asks you to fill in some stuff from the first couple of sentences of the reading. It says outer electrons of the atom in a metal are, and again, you can put loosely bound, or I think it said free roaming, or free loosely attached, something like that, to the nuclei, but are free to roam in the material. All right. So, moving along. Where do we go? So, we're going to look at things like semiconductors. Semiconductors are things that, right, semi means half, right? So half conducting, half not, right? That's what the prefix means. So semiconductors are things that you can basically use as an on-off switch. Half the time, not half the time, but you can have it be on or you can have it be off. These show up in computers. All right, semiconductors, they're on chips. I'll show you a picture. And so they're very useful. There we go. There's one. They're useful in that they can go on, off, and that's what your computer and your phone do. That's what they do all the time. Is they do a series of switching on and off in order to run a program, to do a process, to get you whatever you want, like show you stuff on Instagram. Okay, moving along. Superconductors are things that are that conduct very well at extremely low temperatures, and so low temperatures we're talking about around 100 Kelvin, and that's well below the freezing temperature of water, and electrons flow without any resistance there. Okay, so charging. How do we charge stuff? Well, we already talked about this one. We did this with the straw, and I picked up the pieces of aluminum foil. This is charging by friction and then contact. So here they got this example of this lady sliding across a bench seat in a car as it goes around the corner. And this is like you dragging your feet on the carpet. She builds up a charge. Then she touches the dude, and the charges, the electrons, want to reach equilibrium. So there's more in one than the other. They move until they're equal, and that movement causes a zap. So that's one way to charge. That's charging by contact. Another way to charge is by induction. And this is, again, kind of similar to what you feel here when you get this magnetic touch. So let's explain. If you bring something that's charged near a surface, all right, here we've got two neutral spheres. So we bring something that's negative near, what's going to happen? What gets attracted to negative? Opposites attract, right? So what gets attracted? Positives get attracted. And if the positives all go over here, guess what's going to go over there? Negatives, right? Because the negatives want to get away from this negative here. They're going to move apart. Now, if you keep this here and then you separate these two objects, you now have some things that are charged. This is called charging by induction. You've induced the electrons to move, right? You've induced the electrons to move away from this negative object, and you've induced, well, the protons haven't moved at all, but since lots of the electrons moved, this is now more positively charged and more negatively charged. We could say that these two spheres both had 10 electrons, and now we could say that this one only has 4, and this one now has 16. And I'm saying that because there's 6 negatives here and 6 positives, right? So what do we get? Well, we take this away, and now since these two spheres aren't connected, these electrons can't leap back over here. Now we've got something that's negative and something that's positive. If we were to touch these again, you would see a spark, right? That would be that static electricity shock. But these things are now charged, and if you connect them, energy will want to flow from one side to the other, and you can take advantage of that. This is basically how a battery works. There's pressure to flow across here to equalize, and that pressure is what you can use to power a device. By the way, that pressure, is it called current, voltage, or resistance? It's called voltage. Higher voltage, the higher the pressure. Right? So a 1.5 volt AA battery has 1.5 volts of pressure. A 12 volt car battery, you've seen those can do a lot more. If you touch two pieces of what do you call it, the charging cables, so the jumper cables, you touch those together, it's a big spark. Versus if you touch two wires that are connected to a 1.5 volt AA battery, tiny spark. And if you touched two wires that were connected to your wall outlet, it's 120 volts. That's a huge spark, and it just keeps going bigger. Okay, so here, this is what I was talking about earlier. We've got differently charged spheres here, right? And then when you touch them, they equalize. So, a few different ways to charge things. So, what's the use of all this? Well, again, that now gets back to where I started, and that is the idea of induction charging. And so I've got this cool video that I found about wireless charging. I'm sure it's going to reload. Oh, maybe not. Let's watch it together.
You set this thingy on that thingy, and then bam, power. But how the heck does electricity get from the wall into my phone?
Great question.
Hello, everybody. Trace here for D News. Thanks for stopping by. You're probably watching this show via a device that has a battery. Laptops, mobile phones, toothbrushes, though not this new watch everyone's talking about for some reason. All of these things need charging, and for the moment, we're still using cords and plugs for this. Inductive charging, or wireless charging, isn't new. It's been used since the early 1990s in electric toothbrushes and for surgically implanted devices like artificial hearts. You've even heard of this in pop culture. In the late 1800s, Tesla was allegedly able to power light bulbs with no wires and claimed to be able to transmit power from one location to another wirelessly. This is...
So, Nikola Tesla. Look him up. Very interesting guy. There's even a movie made about him about 10 years ago. It's pretty cool.
Something we can explain, I guess. To make it work relies on simple physics. Have you ever wrapped a coil of wire around a nail and attached a battery in science when you were a kid?
You will soon.
Electricity in the battery runs through the wire, creating an electromagnetic field or flux. Do it at home. It's fun. You can use it to pick up paper clips or whatever. With that same principle, a coil of wire, magnet, battery, you can make it go the other way too. Spin a magnet in a coil and you'll generate electricity by taking that magnetic flux and moving it through that coil to create electricity. The battery creates a stable electromagnet because it's direct current. It's going one way. The power from your walls is alternating current. That changes direction 60 times a second, or it cycles at 60 hertz. So the electrons are moving back and forth. Remember that because that's the key to wireless charging. Wireless inductive charging gets its name from that magnetic field interaction called induction. Inside of the charging pad and the inductive charging device are tiny coils of wire. The pad being plugged into the wall is fully powered, and that power is cycling at 60 hertz a second. When the other coils come within a short distance, their flux will interact with the flux in the device, move the electrons around, and charge the battery.
So in a way, this is kind of like sound and sound waves, right? A speaker over here is vibrating and creating pressure waves, which move to your ear. And let's say your ear is over here. So those pressure waves move over here. And when they get to your ear, they make your ear vibrate. And in much the same way, we've got this electromagnetic flux. It's a Well, it's an electromagnetic wave, and so that is what's causing, it's moving in from one coil and causing the other one to energize. And in essence, in basic terms, that's how you're able to get energy to flow from one spot to another without them actually physically touching. It's through the electromagnetic field. And again, this is kind of similar to what we got going on here. There's a magnet on the end of this, and when I bring it close, it's lining up these little thin pieces of iron called filaments. They're just like, they almost look like pencil shavings, and it lines them up and it makes them come to the surface. And you can even see, you probably can't see on the video, but I can drag some of them around in these little cells. I'm dragging them around, even though I'm not touching them. All right, and that's the magnetic field that's causing them to move. And so basically, if you can get the magnetic field to cause electrons to move, then that's going to build up that pressure, that voltage that we talked about. And then when you release that pressure, that's energy that can be used. So that's essentially what's going on with this inductive charging stuff. Pretty cool stuff. And let me show you what it looks like on the inside. I had a picture here. There we are. So right there, you can see this coil of copper wire, and then there's two wires coming off of it. This is the internals of a phone. And so this is our ring, and that flux, that electromagnetic field, is going to energize this. It's going to cause electrons that are in here to move. And when those move, they push and pressurize the battery, and that builds up the energy in the battery, and then you can use that. That's it. It's cool stuff. And just, simple stuff. It's just a coil of copper. All right, let's continue.
Chances are on a real device, the number of cycles per second isn't going to be 60 hertz, but like 5 or 10, so it doesn't mess up other things in your house. Your Wi-Fi network, for example, cycles at 2.4 gigahertz, or 2.4 billion cycles per second. So that's definitely not going to be messed with, but with all those radio waves flying around, you can't be too careful. But if it's that easy, you'd think that this would be everywhere. But the problem is efficiency. You waste a lot of power filling up two coils and letting them talk to each other. It's so much better to just plug it right in. The future of wireless charging is unclear. It seems like a great idea, but it's still going to be in the short distance game for a little while. In 2006, MIT found if you match the frequencies of those devices, you can make the power go a few meters. So if you were in your living room and the charger port was there, your phone would charge right in your pocket. They're working on marketing the technology now, but it's still not quite ready. Mr. Tesla, we're getting there, man. Speaking of awesome innovations, how about
no? All right, so where is this now? Well, it's not in Starbucks anymore. They got rid of them. The efficiency thing is real. However, if you get the device close enough to the wireless charging pad, it's pretty efficient. Apple's offering these now. I believe you can wirelessly charge your AirPods, and you can, like I said, Tesla and about 50 other cars have wireless charging pads as an option for their vehicles. And so as long as you get close enough, the efficiency is pretty good, and the convenience is definitely worth it. Okay, that's it for the day. Hope you have a great weekend, and see you later.